We shall now prove that the space of p integrable functions on a measure space, they form a Banach space. Namely, we have to prove that this norm vector space is complete. Okay, so what we do, we fix a measure space, and for functions on this set E measurable, we define the p norm, which is the integral of the p power of the function, okay? And we shall consider the functions that for which this norm is finite. If p is infinity, we also defined the norm as the essential sup. So the sup up to a set of measured zero. Then LP, or better LP of this metric of this measure space, is the set of all functions measurable such that the p norm is finite. This is up to the equivalence of being equal almost everywhere. The theorem we're going to prove is that for all p, from 1 included up to plus infinity included, the space LP with this norm is complete. So it forms a Banach space. Okay, let's prove it. Proof. Okay, first let's consider the case where p is not infinity. So p is different than infinity. So take Fn inside LP a Cauchy sequence. We need to prove that it converges. So up to choosing a subsequence, for Cauchy sequence is enough to prove that a subsequence converge. So up to pass into a subsequence, I will not change the index of this of the sequence. We can assume that consecutive elements have p norm less than 4 to the minus n. Okay, and now we consider the set an is the set of points for which the norm of, or like the absolute value between fn plus 1, this is greater than 2 to the minus n. Okay, so therefore, what we can say is that the norm, the p norm of this difference of functions, p norm, since on this set the function have at least this value, we can bound from below 2 to the minus n, because we raise to the p, but then we take the p power, the p root of the measure of an 1 over p. Okay, so which means that now, since we ask for this bound, together with this, we can say that the measure of an is less than, okay, 2 to the n norm of fn minus fn plus 1 norm p to the p power, and put in the first bound, we get that this is less than 2 to the minus np. Yeah. Okay, so now let's consider the set A to be the intersection of all natural n capital N of the union of n greater than capital N of an, which means these are the points that are in infinitely many an. Okay, so what we know is that, okay, what is the measure of this set? Then the measure of set A is equal to the limit, because this is an increasing sequence, sorry, decreasing sequence in capital N. So the measure is the limit of the measures, n, which is now by additive sigma additivity or subadditivity. This is the limit n going to infinity of the sum of the measures, which is minus to the np, and from capital N to infinity, or plus 1. And now this series converges. The series converge, so the tail of the sequence of the series goes to 0. So this limit is 0. So A has measured 0. Good. Okay. Now let's go back to A. A, what's in A? So the points are not in A. It's a full measure set, and these are the set that if they are not in N, it's equivalent to say that there are only infinitely many of the AN. So note that X is not in A if and only if there exist finitely many N for which X is in AN. So for all N, there exist capital N, okay, for all X exists N, depends on X, such that for all N greater than this N, we have that X is in AN, is not in AN, so which means that the value of the difference is less than 2 to the minus n. So for fixed X, this sequence here, form a Cauchy sequence. This means that Fnx as a subset of R is a Cauchy sequence, or is Cauchy. So what we do, we can define the function, so we can take limits for all this x in A. So we define the following function, f of x, to be 0 if x is in A. That's not important because it's zero measure set, let's set it to be 0. Otherwise, we can consider the limit of fnx if x is not in A. So we define a function, and now we're going to check that this function is the limit of the Fn. So the claim is that Fn converges to F in LP. Or, yeah, let's first prove that it converges mu almost everywhere. Okay. So for doing this, let's define an auxiliary function. So define gx to be the function, okay, norm f1 plus the sum n greater than 1 of fnx minus fn plus 1 x. Okay. So this is a definition. Let's consider this function. Okay. So first of all, this function here is measurable. we define in terms of f. And what is the p norm of this function? And if I take the integral of g to the p 1 over p, then okay, this is let me think a second. Okay, so this function is defined with an infinite series. Okay, so let's stop the sequence, this series, to a capital N, and g will be the limit of this sequence. But you see that what we're adding positive terms. So this sequence is monotone in N. So instead of g, I will put the limit when n goes to infinity of f1, let's not put x, modulus of f1 plus the sum from 1 to n of fn minus fn plus 1 to the power p in the mu 1 over p. Okay. Now, since this limit is monotone, it's a monotone sequence, then I can swap the integral with the limit. So I can write it, the limit of n going to infinity of the integral of f1 plus sum of n from n minus 1, from 1 to capital N, fn minus fn plus 1 to the p power the mu 1 over p. Okay, so now so this is the p power, the p norm. Maybe we can write it like this. This is the limit of the norm of this function here. We know that the norm, by the Minkowski inequality, is a norm. So the norm of these finitely many vectors, this is a finite sum, we can write it, or we can bound it as the sum of the norms. This I can write it as f1, I can remove the absolute value, plus the sum from 1 to n of fn minus fn plus 1 p power. Good. Now, what we had that this LP norm was less or equal than 4 to the minus n, which means that this series converges to a finite value. This is also finite. So what we understood is that this bound, that we got, is finite. In other words, what we proved is that G is in LP, or the P power, but the P norm of G is finite. Okay, so what we want to do, we want to use G, that now is P integrable, to dominate the function, the sequence of function Fn, and therefore pass to the limit in the integral. So notice, so every Fn is bounded by G. So yeah, and Fn is bounded by G. So, okay, they're integrable. The p power is also in, so now if I take the p power now, these are all integrable. So the integral of Fn is bounded by the integral of G. So we have a domination, and therefore so Gp dominates Fn, but also dominates the sequence Fn minus f to the p, just by bounding each of the two functions. Maybe we have to put 2 to the p, because we have two terms. Okay, so what we get the limit of the integral of Fn minus f to the p, so the p norm of this difference, by the dominated convergence theorem. We can swap the integral with the limit n minus f p d mu, and this is equal to 0. Okay. Let me better explain why Fn converges to f almost everywhere. So one should modify a little bit this argument. So one should define a function gk summing from k the from fk onward these differences. Then what we get is that the same calculation that we did give us a bound that is infinitesimal, right? So which means that not only this number is finite, but it's as small as we want. So as k goes to infinity, okay, this was less than 2 to the k. We have to assume this. So okay, right, no, the difference is as close as f to the k. So this quantity is infinitesimal. So from this one gets that the difference Fn minus f in is integrable, and with arbitrary small integral. So which means that in norm Fn converges to f. Okay. Okay, good. Let's move on and let's study the case p equal to infinity, which is actually much easier, because one can do like this. So for all epsilon, one can consider the n for which so we have a Cauchy sequence. So for n, all n m greater than n, the supremum of fnx minus fmx when x is in the space E, then this is smaller than epsilon. And this is true. So we have to take a representative of f, and this is, and maybe we have to change f. This we know that has a limit. This is a Cauchy sequence on a fn on a null set. Okay. Now, for an x in E, we again get that fnx as a sequence of n is Cauchy, and therefore there exists a limit function f. And because of this bound here, we have that f is bounded, and so in L infinity. Okay, now I leave for you to check that f minus f infinity, the fn in norm infinity, this converges to 0. Okay, so to summarize this proof, what we did is to show that a Cauchy sequence in LP converges to a function LP. We use the fact that evaluated at a point, this gives a Cauchy sequence in the real line to construct a function. And then we get a dominated bound for the functions and for the difference to show that the convergence is also in LP. We're going now to prove an inequality between norms of functions due to Hölder. This inequality is very useful in many situations. The first use we'll make it is to see how LP as dual LQ for a very precise Q. Now this is the inequality. So this is a theorem due to Hölder. So let PQ in 1 infinity such that the inequality that we need to have is 1 over P plus 1 over Q should be equal to 1. Or if P is 1, then we take Q to be infinity. So both cases are okay to us. So then what the inequality says that we can integrate the norm, the absolute value of the product FQ with respect to the measure, and this can be bounded by the norm, the P norm of F times the Q norm of G. This, of course, as soon as they're finite, otherwise, okay, it's true, but it's useless. So if these two norms are finite, then this is meaningful and say that this product of the two norms bounds this integral. You should think of this as a generalization of the Cauchy-Schwarz, right? When P is 2, Q is also 2, and then what you're saying is that the scalar product between F and G, of course, you can remove this absolute value, because of course you can always take the absolute value of F and absolute value of G, and these terms stay the same, and they are still in LP and LQ. So the scalar product in L2 is bounded by the norms of the vectors. This is a generalization of this fact. So this is a theorem, and let me stress that there is this duality between these two exponents. So given P, there exists, and it's actually unique, a Q as above, so that satisfy this, right? And so these two numbers, and of course they are in duality, one of them defines the other, and this Q is called conjugate exponent and sometimes this is denoted by P star, kind of dual to P. And notice that P star star is equal to B to P. Okay. Let's prove the Hölder inequality. So proof. Okay. First, let's do the case P equal 1 and Q equal plus infinity. So this is quite an easy case. Then the G, the absolute value of G, is bounded by the essential sup. This is almost everywhere, and one can bound there. Therefore, Fg, the mu, one can bound it as absolute value of F, essential sup of G, the mu. Now this is a number, so we can move it outside. This is G infinity, F the mu, so it's infinitum of G, L1 norm, L1 norm of F. So we obtain the desired inequality. Second case, let's consider both of them finite, infinity. And of course, we may assume that they are not zero almost everywhere, which is the same of saying that their norm is non-zero. So we may suppose norm of F, P, norm of G, or Q norm of G to be different than zero. Now, what we are going to use the concavity of logarithm. So the logarithm function is a concave function, right? So this is the, right? So if you take 2 points, X and Y, so what you take the value, then the line between the values is below the graph of the function, which means that for all X and Y positive real numbers, and for all lambda in 0, 1, we have that the logarithm of lambda x plus 1 minus lambda y is greater or equal, this is the point in the graph, is above the line log x plus 1 minus lambda log y. Okay. Now what we are going to do, we are going to choose lambda to be 1 over p. So what we are going to get is that 1 minus lambda is equal to 1 over q. And we take exponentials. So what we get 1 over px plus 1 minus 1 over qy is greater or equal to e 1 over p log x plus 1 over q log y. So now this exponent pass here as an so this number becomes an exponent in x, this one becomes an exponent in y. E to the sum is the product of the exponents, and what we get x to the 1 over p times y 1 over q. Okay, so now we're going to take x to be norm of absolute value of f to the p divided by the p norm the p power of the p norm of p, and y, similarly, the absolute value of g to the p divided by the, so the q, and then the q power of the q norm of g. And we put it inside, what we get is 1 over p fp divided by the norm to the power p of f plus 1 over q norm of g to the q, so the absolute value of q. Now below there is the q power of the q norm. This is greater or equal the norm of fg divided by okay, q, the norm of f p, the norm of g, right? Because these exponents kill these exponents. Okay, we are almost done. Now we integrate. Integration gives, okay, if I integrate this, then obtains exactly the p power of the p norms of f. So we divided by this, it gives 1. Similarly, the integration of this function gives me exactly this number. So what I get, integrating the term on the left, is 1 over p plus 1 over q, which is equal to 1. The other side, I get these two are numbers, so it's 1 over p norm of f, q norm of g, the integral of f g d mu, which, moving this on this other side, gives the desired inequality. So we proved Hölder inequality.